So what makes a parallelogram a parallelogram? It's a quadrilateral with 4 sides, and it's special because both sets of opposite sides are parallel, hence the name. So both sets, opposite sides, parallel. And because of that definition, that's our definition, we have a ton of properties that follow from that. You can prove that both sets of opposite sides are congruent. So I'm just going to say both, like both sets, opposite sides congruent. And I can also say that both sets of opposite angles are congruent. So both sets, opposite angles congruent. So this one's congruent to that one, and this one's congruent to that one, but they're not all necessarily congruent to each other. You can definitely tell this is acute. That's obtuse. Cool. Here we go. And then we also know that the diagonals bisect each other. So diagonals bisect each other, and that means that this guy cuts that guy in half, so this is congruent to that, and this guy cuts that guy in half, so this is congruent to that. Now notice they're not all the same because this diagonal is longer than that diagonal. So there we go. So these are all the properties of a parallelogram. Turns out they're all reversible. The converses are true, so these are all ways to prove something's a parallelogram. So if you can prove the diagonals bisect each other in a quadrilateral, it'll be a parallelogram. If you can prove the opposite angles are congruent, then it'll be a parallelogram. So if you don't want to prove it by the definition, any one of these will do. You also have if one set is one set of sides is both parallel and congruent. If you can prove that, that'll prove that it's a parallelogram. So best way is by the definition, but a lot of times it's faster to use one of these theorems. All right, so now we get to special sorts of parallelograms. So a special parallelogram is a rectangle. We're all familiar with rectangles, although when we come across them in geometry, sometimes we forget that we know what they are. So it's a beautiful looking rectangle there. But a rectangle is definitely a parallelogram because both sets of opposite sides are parallel. But it's special in that all the angles are congruent. So by definition, a rectangle is a parallelogram with all the angles congruent, and therefore 90 degrees, right? And because of that, we have all these nifty properties. So here, when you draw the diagonals, they're actually congruent, which is very cool. So the diagonals are congruent, which means that because it has all these properties in addition, they actually are all the same, all those little pieces for a rectangle, and all sorts of nifty little things come from that. Those are the main two that you need to know, and then everything else kind of evolves from there. Excellent. So a diagonal has all angles congruent. Then we get to a more exotic figure, the rhombus. And a rhombus is just a parallelogram where all the sides are congruent. Oh, go fig. So all the sides are congruent. So again, it is a parallelogram. Both sides are parallel, and thus it has all of those properties plus more. So this is the definition property. And then in addition to that, it's got some neat ones, these rhombi. So if we draw the diagonals, they are actually perpendicular to each other. So they make all these right angles in the corner. So diagonals perpendicular to each other. And another nifty thing about the diagonals of rhombi is that they bisect the angles. So diagonals bisect angles. So therefore we know that, and because that's combined with the idea of that it's a parallelogram and this angle is congruent to that angle, then we know all of these pieces are the same. And we know that all of these pieces are the same, which is very, very cool. So we've got those. And if the rhombus and the rectangle came together and had a kid, it would be a square. And we know squares, one of the first shapes we learn. It's both a rectangle because all the angles are congruent, and a rhombus because all the sides are congruent. So it has every single property you see on this board. So I'm not going to bother to write any new special ones because they all fall from there. There's nothing really special except it's super special. It's got all that stuff. So those are our parallelograms. And so it's interesting to note, so these are all parallelograms, and we could go off and do other sorts of special types of quadrilaterals. We could do trapezoids, and trapezoids have exactly one set of parallel sides. So parallelogram has both sets of sides that are parallelogram. Trapezoids just have one set of parallel sides. So maybe something like this, or maybe something like maybe a right trapezoid where this guy's parallel to that guy. Or maybe a funky one where like this one is there and this one's super long and that side's parallel to that side. Any one of those will do. It'll be an isosceles trapezoid, we call it, if those legs are congruent. So if those legs are congruent, that's a special type, subcategory isosceles. It's getting a little messy, but you get the idea. Another special kind of type of quadrilateral that you'll see is a kite. So kites are such that they have two sets of adjacent sides congruent. So two sets of adjacent sides congruent. So this guy's congruent to that guy's congruent to that guy. Now, if they all were congruent, then the kite would be a rhombus. So in fact, a rhombus is, some people say that these have to be distinct, that this can't be congruent to that. But there are other definitions where it's okay to say that they're just all the same, like this is congruent to that and that's congruent to that and they're all the same. So then by that definition, a rhombus would always be a kite. But anyway, so that's that. Two sets of adjacent sides, and you've got some nifty properties of kites. If you draw these diagonals, just like rhombi, they make a little, all those diagonals are perpendicular, and then that diagonal will bisect the angle. So these guys are going to end up all being the same. But these guys not necessarily, right? You can definitely see it. Like let's say I started to draw a kite, and I started to draw this like this, and then I decided to draw this big kite where this guy is not congruent to that guy, and then you have other other angles that you can draw. I'm trying to do this too fast. But you can draw all sorts of different kites here where you can see that this angle doesn't rely on that angle. So there's no reason why these have to be the same. So never assume half. It's such a temptation, and all my students want to assume that things cut each other in half. It's just, oh, it cuts each other in half. But you better have a good reason for it to cut, if you assume things are half. You have to have a reason. Don't assume. That's the whole gist of geometry. The high school geometry is for everything you say, you have to have a reason for it. So anyway, that's my little rant on that. But I mainly wanted to get through those guys, and there you have it.